Higher-order functions. The use of higher-order functions is also essential to functional programming. We've already mentioned higher-order functions, and we've even used a few in this chapter. Higher-order functions are functions that can manipulate other functions. They can take functions in as arguments, or return functions, or both. The first category of higher-order functions are functions that expect other functions as arguments. Array.map, array.filter, and array.reduce all take functions as arguments. They are higher-order functions. 3. Let's take a look at how we can implement a higher-order function. In the following example, we create an invoke if callback function that will test a condition and invoke on callback function when it is true and another callback function when that condition is false. Const invoke if equals condition, fn true, fn false equals condition, fn true, fn false. Const show welcome equals console.log welcome. Const show unauthorized equals console.log unauthorized. Invoke if true, show welcome, show unauthorized / welcome. Invoke if false, show welcome, show unauthorized / unauthorized. Invoke if expects two functions, one for true and one for false. This is demonstrated by sending both show welcome and show unauthorized to invoke if. When the condition is true, show welcome is invoked. When it is false, show unauthorized is invoked. Higher order functions that return other functions can help us handle the complexity ties associated with asynchronicity in JavaScript. They can help us create functions that can be used or reused at our convenience. Currying is a functional technique that involves the use of higher-order functions. Currying is the practice of holding on to some of the values needed to complete an operation until the rest can be supplied at a later point in time. This is achieved through the use of a function that returns another function, the curried function. The following is an example of currying. The user logs function hangs on to some information, the username, and returns a function that can be used and reused when the rest of the information the message is made available. In this example, logmes sages will all be prepended with the associated username. Notice that we're using the getForKeyMembers function that returns a promise from chapter 2. Const user logs equals username equals message equals console.log username message. Const log equals user logs grandpa 23. Log attempted to load 20 fake members. GetForKeyMembers 20.then. Members equals log successfully loaded members.length members. Error equals log encountered an error loading members. / grandpa 23 attempted to load 20 fake members. / grandpa 23 successfully loaded 20 members. / grandpa 23 attempted to load 20 fake members. / grandpa 23 encountered an error loading members. User logs is the higher order function. The log function is produced from user logs, and every time the log function is used, grandpa 23 is prepended to the message. Recursion is a technique that involves creating functions that recall themselves. Often when faced with a challenge that involves a loop, a recursive function can be used instead. Consider the task of counting down from 10. We could create a for loop to solve this problem, or we could alternatively use a recursive function. In this example, countdown is the recursive function. Const countdown equals value, fn equals value. Return value, 0. Countdown value 1, fn value. Countdown 10, value equals console.log value. //10. //9. //8. //7. //6. //5. //4. //3. //2. //1. //0 countdown expects a number and a function as arguments. In this example, it is invoked with a value of 10 and a callback function. When countdown is invoked, the callback is invoked, which logs the current value. Next, countdown checks the value to see if it is greater than 0. If it is, countdown recalls itself with a decremented value. Eventually, the value will be 0 and countdown will return that value all the way back up the call stack. Browser call stack limitations. Recursion should be used over loops wherever possible, but not all JavaScript engines are optimized for a large amount of recursion. Too much recursion can cause JavaScript errors. These errors can be avoided by implementing advanced techniques to clear the call stack and flatten out recursive calls. Future JavaScript engines plan to eliminate call stack limitations entirely. Recursion is another functional technique that works well with asynchronous processes. Functions can recall themselves when they are ready. The countdown function can be modified to count down with a delay. This modified version of the countdown function can be used to create a countdown clock. Const countdown equals value, fn, delay equals 1000 equals value. Return value, 0. Set timeout equals countdown value 1, fn, delay. Value. Const log equals value equals console.log value. Countdown 10, log. In this example, we create a 10-second countdown by initially invoking countdown once with the number 10 in a function that logs the countdown. Instead of recalling itself right away, the countdown function waits 1 second before recalling itself, thus creating a clock. Recursion is a good technique for searching data structures. You can use recursion to iterate through subfolders until a folder that contains only files is identified. You can also use recursion to iterate through the HTML DOM until you find an element that does not contain any children. In the next example, we will use recursion to iterate deeply into an object to retrieve a nested value. Var dan equals type person, data, gender male, info, ID 22, full name, first Dan, last Deacon, depic type, Dan, // person, depic data.info.fullname.first, Dan, // Dan. Depic can be used to access Don's type, stored immediately in the first object, or to dig down into nested objects to locate Don's first name. Sending a string that uses dot notation, we can specify where to locate values that are nested deep within an object. const deeppick equals fields, object equals. Const first, remaining equals fields dot split dot. Return remaining dot length. Deeppick remaining dot join dot, object first. Object first. The deeppick function is either going to return a value or recall itself, until it eventually returns a value. First, this function splits the dot-notated fields string into an array and uses array destructuring to separate the first value from the remaining val. Use. If there are remaining values, deeppick recalls itself with slightly different data, allowing it to dig one level deeper. This function continues to call itself until the fields string no longer contains dots, meaning that there are no more remaining fields. In this sample, you can see how the values for first, remaining, and object first change as deeppick iterates through. Deeppick data.info.fullname.first, dan, / deacon. / first iteration. / first equals data. / remaining dot join dot equals info.fullname.first. / object first equals gender male, info. / second iteration. / first equals info. / remaining dot join dot equals fullname dot first. / object first equals ID 22, fullname. / third iteration. / first equals fullname. For functional.js composition. / remaining dot join dot equals first. / object first equals first dan, last deacon. / finally. / first equals first. / remaining dot length equals 0. / object first equals deacon. Recursion is a powerful functional technique that is fun to implement. Use recursion over looping whenever possible. Composition functional programs break up their logic into small pure functions that are focused on specific tasks. Eventually, you will need to put these smaller functions together. Specifically, you may need to combine them, call them in series or parallel, or compose them into larger functions until you eventually have an application. When it comes to composition, there are a number of different implementations, patterns, and techniques. One that you may be familiar with is chaining. In JavaScript, functions can be chained together using dot notation to act on the return value of the previous function. Strings have a replace method. The replace method returns a template string which also will have a replace method. Therefore, we can chain together replace methods with dot notation to transform a string. Const template equals HHMMSSTT. Const clock time equals template dot replace HH 03. Dot replace millimeter 33. Dot replace SS 33. Dot replace TT PM. Console.log clock time / 033333 PM. In this example, the template is a string. By chaining replace methods to the end of the template string, we can replace hours, minutes, seconds, and time of day in the string with new values. The template itself remains intact and can be reused to create more clock time displays. Chaining is one composition technique, but there are others. The goal of composition is to generate a higher order function by combining simpler functions. 4. Const both equals state equals, append of Machiavellian Hauer state. 5. Another implementation of compose is found in Redux. The both function is one function that pipes a value through two separate functions. The output of civilian hours becomes the input for append AMPM, and we can change a date using both of these functions combined into one. However, this syntax is hard to comprehend and therefore tough to maintain or scale. What happens when we need to send a value through 20 different functions? A more elegant approach is to create a higher order function we can use to compose functions into larger functions. Const both equals compose. Civilian hours, append AMPM. Both new date. This approach looks much better. It is easy to scale because we can add more functions at any point. This approach also makes it easy to change the order of the composed functions. The compose function is a higher order function. It takes functions as arguments and returns a single value. Const compose equals, fns equals, arg equals, fns.reduce. Composed, f equals, composed, arg. Compose takes in functions as arguments and returns a single function. In this implementation, the spread operator is used to turn those function arguments into an array called fns. A function is then returned that expects one argument, arg. When this function is invoked, the fns array is piped starting with the argument we want to send through the function. The argument becomes the initial value for composed and then each iteration of the reduced callback returns. Notice that the callback takes two arguments composed and a function f. Each function is invoked with compose, which is the result of the previous function's output. Eventually, the last function will be invoked and the last result returned. This is a simple example of a compose function designed to illustrate composition techniques. This function becomes more complex when it is time to handle more than one argument or deal with arguments that are not functions. Other implementations of compose 5 may use reduce write, which would compose the functions in reverse order. Putting it all together, now that we've been introduced to the core concepts of functional programming, let's put those concepts to work for us and build a small JavaScript application. Since JavaScript will let you slip away from the functional paradigm, and you do not have to follow the rules, you will need to stay focused. Following these 3 simple rules will help you stay on target. 1. Keep data immutable. 2. Keep functions pure, accept at least one argument, return data or another function. 3. Use recursion over looping wherever possible. Our challenge is to build a ticking clock. The clock needs to display hours, minutes, seconds, and time of day in civilian time. Each field must always have double digits, meaning leading zeros need to be applied to single-digit values like 1 or 2. The clock must also tick and change the display every second. First, let's review an imperative solution for the clock. // log clock time every second, set interval of clock time, 1000. Function log clock time. / get time string civilian time var time equals get clock time. / clear the console and log the time console.clear. Console.log time. Function get clock time. / get the current time var date equals new date. Var time equals / serialize clock time var time equals hours date dot get hours, minutes date dot get minutes, seconds date dot get seconds, ampman. / convert to civilian time. If time.hours equals 12. Time.am equals PM. Else if time.hours 12. Time.am equals PM. Time.hours equals 12. / prepend a 0 on the hours to make double digits if time.hours. Time.hours equals 0 time.hours. / prepend a 0 on the minutes to make double digits if time.minutes. Time.minutes equals 0 time.minutes. / prepend a 0 on the seconds to make double digits if time.seconds. Time.seconds equals 0 time.seconds. / format the clock time as a string HHMMSSTT. Return time.hours. Time.minutes. Time.seconds. Time.amp. This solution is pretty straightforward. It works, and the comments help us understand what is happening. However, these functions are large and complicated. Each function does a lot. They are hard to comprehend, they require comments, and they are tough to maintain. Let's see how a functional approach can produce a more scala BLE application. Our goal will be to break the application logic up into smaller parts, functions. Each function will be focused on a single task, and we will compose them into larger functions that we can use to create the clock. First, let's create some functions that give us values and manage the console. We'll need a function that gives us 1 second, a function that gives us the current time, and a couple of functions that will log messages on a console and clear the console. In functional programs, we should use functions over values wherever possible. We will invoke the function to obtain the value when needed. Const 1 second equals 1000 const get current time equals new date. Const clear equals console.clear. Const log equals message equals console.log message. Next we will need some functions for transforming data. These 3 functions will be used to mutate the date object into an object that can be used for our clock. Serialize clock time takes a date object and returns an object for clock time that contains hours, minutes, and seconds. Civilian hours takes the clock time object and returns an object where hours are converted to civilian time. For example, 1300 becomes 1 o'clock. Append AM PM takes the clock time object and appends time of day, or PM, to that object. Const serialize clock time equals date equals hours date dot get hours, minutes date dot get minutes, seconds date dot get seconds. Const civilian hours equals clock time equals clock time, hours clock time dot hours, 12. Clock time dot hours, 12. Clock time dot hours. Const append AM PM equals clock time equals Clock time, and clock time dot hours, equals 12 p.m. These three functions are used to transform data without changing the original. They treat their arguments as immutable objects. Next we'll need a few higher order functions. Display takes a target function and returns a function that will send a time to the target. In this example, the target will be console.log. Format clock takes a template string and uses it to return clock time formatted based upon the criteria from the string. In this example, the template is HHMMSSTT. From the format clock will replaces the placeholders with hours, minutes, seconds, and time of day. Prepend 0 takes an object's key as an argument and prepends a 0 to the value stored under that object's key. It takes in a key to a specific field and prepends values with a 0 if the value is less than 10. Const display equals target equals time equals target time. Const format clock equals format equals time equals format dot replace HH time dot hours dot replace millimeter time dot minutes dot replace SS time dot seconds dot replace TT time dot am. Const prepend 0 equals key equals clock time equals clock time key clock time key 0 clock time key clock time key. These higher order functions will be invoked to create the functions that will be reused to format the clock time for every tick. Both format clock and prepend 0 will be invoked once, initially setting up the required template or key. The inner functions that they return will be invoked once every second to format the time for display. Now that we have all of the functions required to build a ticking clock, we will need to compose them. We will use the compose function that we defined in the last section to handle composition. Convert occuvillion time, a single function that will take clock time as an argument and transforms it into civilian time by using both civilian hours. Double digits, a single function that will take civilian clock time and make sure the hours, minutes, and seconds display double digits by prepending zeros where needed. Start ticking starts the clock by setting an interval that will invoke a callback every second. The callback is composed using all of our functions. Every second the console is cleared, current time obtained, converted, civilianized, formatted, and displayed. Const convert occuvillion time equals clock time equals compose. Append AM PM, civilian hours. Clock time. Const double digits equals civilian time equals compose. Prepend 0 hours, prepend 0 minutes, prepend 0 seconds. Civilian time. Const start ticking equals set interval. Compose. Clear. Get current time, serialize clock time, convert occuvillion time, double digits, format clock HHMMSSTT, display log. 1 second. Start ticking. This declarative version of the clock achieves the same results as the imperative version. Sure. However, there are quite a few benefits to this approach. First, all of these functions are easily testable and reusable. They can be used in future clocks or other digital displays. Also, this program is easily scalable. There are no side effects. There are no global variables outside of functions themselves. There could still be bugs, but they will be easier to find. In this chapter, we've introduced functional programming principles. Throughout the book, when we discuss best practices in React and Flux, we will continue to demonstrate how these libraries are based in functional techniques. In the next chapter, we will dive into React officially with an improved understanding of the principles that guided its development. 1. Ben Alpert, React version 0.14, React blog, the 7th of October, 2015. Chapter 4 Pure React. In order to understand how React runs in the browser, we will be working purely with React in this chapter. We will not introduce JSX or JavaScript as XML until the next chapter. You may have worked with React in the past without ever looking at the pure React code that is generated when we transpile JSX into React. You can successfully use React without looking at pure React. However, if you take the time to understand what is going on behind the scenes, you will be more efficient, especially when it comes time to debug. That is our goal in this chapter, to look under the hood and understand how React works. Page setup. In order to work with React in the browser, we need to include two libraries, React and React DOM. React is the library for creating views. React DOM is the library used to actually render the UI in the browser. React DOM React and React DOM were split into two packages for version 0.14. The release notes state: the beauty and